Wrong. There we go. Sorry. All right. Hello, everybody. Welcome to the Ghost Systems Verification Results webinar. My name is Zach Hartman. I'm a science fellow at Gemini North, working on a bunch of things, but one of the things that I'm really getting involved in now is user engagement. And so I am pleased to have all of you here today to listen to two talks about the results of the Ghost science verification. And so we're going to start off first with Christian Hayes. So if you want to share your screen, we can then go.
Great. Hopefully everybody will be able to see this momentarily. All right. Can everybody see that?
Yeah, actually,
hear me all right?
Let me mention one thing. If you have questions, please put them in the chat. We'll address questions after each talk. And then if you have further questions, then we can open it up for more general discussion.
Great. Well, thank you, everybody. I'm excited to talk to you all today. My name is Chris Hayes. I'm a postdoc at the Hertzberg Astronomy and Astrophysics Research Center in Victoria, Canada. And I'm excited to talk about some of the Ghost systems verification results, particularly something that I'm very interested in, which is investigating the chemistry of a dwarf galaxy, Crater 2. And of course, I do want to say thanks to the entire Ghost systems verification team, because without them, obviously, none of this would have been possible. And thanks as well to Gemini for putting this whole program together and showcasing what Ghost can actually do. So first, I want to start off with a little bit of background. So the Crater 2 is an interesting dwarf galaxy because it's very large, but very low density. And so what I'm showing here on the right is absolute magnitudes of Milky Way and Andromeda satellites as a function of their physical size in terms of their half-light radius. And so with really small systems, you have things like clusters, and with larger systems, you have dwarf galaxies. And dwarf galaxies are now sort of split between what we call classical dwarf spheroidals and ultra-faint dwarf galaxies, which is sort of divided at an absolute magnitude of about -7.5. And Crater 2 sort of sits right in between the two. And the interesting thing, particularly about Crater 2, is that it's very large. So it has a size that's about the same as the SMC, but it is about 7.5 magnitudes fainter than the SMC, making it about 1/1000th its luminosity. And so it's a very large system, which is kind of odd. And it falls in between these sort of absolute magnitudes of classical dwarf spheroidals and ultrafaints. Now, this is sort of an arbitrary division, but in reality, there's a little bit of truth to some sort of dividing line between these two. Dwarf spheroidals typically have higher masses, higher metallicities, and more extended star formation histories. So they have star formation histories that can last, a few billion years or so. Ultra-faint dwarf galaxies are lower mass, lower metallicity, and typically have a star formation history that ends somewhere around the point of reionization. Crater 2 is typically sort of put on the classical dwarf spheroidal side of things, and in part, its sort of very large size helps put it in that field. It's not quite clear why it's so large, but one of the possible explanations is that it's being tidally disrupted. And so one of the observations is that it also has a very low velocity dispersion. So this shows circular velocities as a function of these half-light radii. And these circular velocities are sort of proportional to the velocity dispersion of a system. And you can see that Crater 2 sits down here in the sort of the bottom left-hand corner of this diagram, which shows a whole bunch of other satellite dwarf galaxies of the Milky Way and Andromeda. Now, this is sort of interesting because lambda CDM cosmological simulations would suggest that isolated dwarf galaxies typically fall within this sort of gray band up here. And as soon as they start to fall into Milky Way or Andromeda-like halo systems, tidal stripping will sort of bring them down into this blue region down here. And Crater 2 actually sits even further below that. So it's a bit at odds with what we would typically expect from cosmological simulations. Now, there's a few different ways that you can explain this. Lambda CDM cosmological simulations tend to say that dwarf galaxies have these cuspy dark matter distributions. So the dark matter density increases as you go into the center of the dwarf galaxy. all the way down to the very center. Whereas some observations suggest that they might have chord profiles, so the densities actually flatten off as you get towards the center. And this can possibly happen if you have a lot of baryonic matter in the center of your galaxy that sort of smooths out the dark matter distribution. But to actually prove that would require showing that Crater 2 has had tidal interactions with the Milky Way in the past and lost mass. So it's a sort of interesting galaxy to explore how the dark matter exists in this galaxy. But another way, unfortunately, the main way that you would go about doing this would be to look for tidal streams around the system. But none have been detected for Crater 2. So another way that you can go about sort of understanding what its mass may have been in the past is to look at its chemical enrichment and star formation histories. And so the interesting observation about Crater 2 in this aspect is that there's actually evidence for an age spread in Crater 2, which we might be able to use from a spectroscopic point of view to understand its evolution. This shows a color magnitude diagram here on the right of the inner region of Crater 2. And you can see the main sequence of Crater 2, its red giant branch and horizontal branch, buried in some Milky Way contamination. The interesting thing is that you can actually see a bit of a split in its main sequence turnoff, which suggests an age spread. And isochrone modeling suggests that there's about a 2 billion year spread in sort of ages in Crater 2. And this is useful because of the fact that there are chemical evolution tracers that should actually have observables for an age spread like this that might be able to help us tie a mass to this system. And to give you an idea of why that is, it's because some elements are produced in prompt sources of supernovae, like core collapse supernovae that happen right after a star formation event, such as alpha elements, the even numbered elements from, say, oxygen up to titanium, which includes things like magnesium, silicon, calcium, titanium, oxygen. Whereas some elements like iron can be produced not only in core collapse supernovae, but also type 1a supernovae, the explosive deaths of white dwarfs. And these almost exclusively produce iron and similar elements around it in the periodic table. So alpha to iron ratios can tell you about the ratio of core collapse supernovae to these type 1a supernovae, with the difference being that type 1a supernovae take about 1 billion years before they really start contributing to the chemical enrichment of a galaxy. And so that's what this is showing over here. It's showing alpha to iron ratios as a function of metallicity. And this is on a logarithmic scale where the sun, which is relative to the sun. So the sun is at 0, and -1 would be 1/10 of solar, -2 would be 1/100th, and so on. And this shows some model chemical evolution tracks on the left, as well as mock observations with sort of typical abundance uncertainties on the right. A galaxy will typically start at low metallicities and begin enriching. It'll start out with a high alpha to iron ratio because it's only got core collapse supernovae. And then after about 1 billion years, it will turn on its type 1a contribution, and you will see a decrease in alpha to iron ratios. And the point at which this knee happens is somewhat tied to the mass of the system. So for instance, this shows a Milky Way-like model and a dwarf galaxy model. So the Milky Way would be much more massive, and its knee is at a higher metallicity. And so we can actually see that this entire chemical abundance pattern shifts to lower metallicities if you're a less massive system. And we can use this sort of concept to at least place Crater 2 in sort of the rank ordering of masses of galaxies, of dwarf galaxies in the Milky Way halo, and get a better idea of if it looked like a more massive system in the past. And so that's where GHOST comes in. So with GHOST, we can measure a whole bunch of different chemical abundances. And so what we did was we took, just to look and see if we have evidence for type 1a contribution in Crater 2, we wanted to get a spectra of 2 stars in Crater 2, which I'm showing a portion of their GHOST spectrum here, both in the black spectra, or the black lines here. The gray line down here is just sort of a reference star that's a metal poor giant star for that we can observe at high resolution and high signal to noise for comparison, so that you know where all of these features are. And this is looking at a portion of the GHOST spectrum around what's called the magnesium B triplet, which are these 3 strong magnesium lines. And we can see a whole bunch of different features. Just for some numbers, for those who are interested in maybe using GOEST in the future, this is 2 stars that are about 17.5 in Gaia G-band magnitudes. We observed these for 40 minutes each in GOEST single target standard resolution mode, which has a resolution of about 50,000, using a 2 spectral binning and a by 8 spatial binning. But we can measure a whole bunch of different lines in this region, even with the relatively lower signal to noise that we've got. So in this region in particular, this is a signal to noise of something like 14, 15. And some of the other signal to noise in different regions that are interesting for chemical abundance analyses are shown below, but I'll just continue to focus on this one. We can see all of these different lines coming from iron, titanium, magnesium, calcium, and we can actually measure the chemical abundances from these lines. And we do so using what we call spectral synthesis. So what we've done is we've measured a whole bunch of different lines. We compare the observations with model spectra with different chemical abundances. So in this case, what you can see is 3 titanium lines here in the middle of each of these panels. The solid red shows the best fit titanium abundance for each of these for the star, and the dashed red lines show a 0.3 dex range around that best fit. The blue, for reference, shows what would happen if you had no titanium in the star. And so you can see we clearly can measure these lines, and the fits look relatively reasonable. We can do this for a number of different elements, and I'm just going to focus on 3 of them here. I'm going to focus on 3 alpha elements, calcium, magnesium, and titanium. So I've got plots here that show the magnesium to iron, calcium to iron, and titanium to iron abundances as a function of metallicity. These plots show these 2 stars in crater 2 highlighted in the red symbols, as well as Milky Way field stars in the background in gray, and ultra-faint dwarf galaxy stars in the colored points. And what we can observe just right away, just looking at the measurements for these stars, is that they have roughly solar alpha to iron ratios in these 3 elements, or sometimes even subsolar. And this suggests right off the bat that type 1a supernova is a reasonable explanation for these low alpha to iron ratios. But on top of that, we can compare it with other systems. So for instance, comparing with the Milky Way halo, where we think that we don't have any type 1a contribution, we can see that it has a much lower alpha to iron ratio in a bunch of these elements. But we can also see that it sort of sits at the lower end of the alpha to iron ratios that are covered by ultra-faint dwarf galaxies in these colored points. The one exception to that being Carina 2, these sort of teal colors, which is another system where we think that we've got some evidence for, we might have evidence for type 1a contributions. But what's more interesting is comparing to some of the more massive dwarf galaxies in the Milky Way. For instance, Sculptor and Sextans. Sculptor is a little bit more massive than Sextans, and so you can see in its alpha to iron abundance patterns, it's actually slightly more metal rich. So Sextans looks like it's slightly shifted to lower metallicities, but nonetheless, these all go to very low alpha to iron ratios, solar and subsolar, even in the case of something like titanium, which is where we're seeing these observations of the 2 crater 2 stars that we looked at. And in fact, these crater 2 stars actually look very similar in their abundances to Sextans, which is a more massive dwarf galaxy than crater 2 is today. And so this gives us a little bit of promise that these stars do look like they have enrichment from type 1a supernovae. And if we build up a larger sample of stars in crater 2, we might actually be able to map out its abundance patterns and sort of place it on a similar scale like we can with other dwarf galaxies. So what I just want to summarize is that these observations with GOEST for crater 2 suggest that for the first time, we can see that this galaxy has evidence for being enriched by type 1a supernovae, which is consistent with the age spread that we can see in crater 2, making it more like classical dwarf spheroidal galaxies than ultrafaints. And future observations with larger samples of crater 2 can actually start to show us what its chemical abundance pattern looks like and may help us place it sort of in the mass ranking of Milky Way satellites. And the final takeaway that I want to leave you with is that hopefully you've taken away that GOEST is a powerful new tool for studying the chemistry of stars, both in the Milky Way and its dwarf galaxies. So with that, thank you, and I'd be happy to take any questions.
All right, thank you very much. Yeah, if you have any questions, please either put them in the chat or raise your hand and I will call on you. So I guess I had one. If you go, you had I think it was titanium
Mhm.
spectra.
Titanium lines.
Yeah.
Yeah.
So it looks like, so without titanium, there's a line that's kind of blended into.
Mhm.
Yeah, which one? What line is that? Sorry, I'm not familiar with
I would have to double check what that is. I think that might actually be a calcium line.
Okay.
If I remember correctly, I think that's actually, I think I chose this one specifically for this purpose. So it's at 5189, which is calcium blend.
Okay.
Yeah.
Awesome. So we have a couple questions from Gary. What's your signal to noise per binned pixel?
So that would be it depends on what spectral range you're interested in. So these, I forgot to say, are the signal to noise per pixel, which is per binned pixel. So in this particular region, it's about signal to noise of 15 per pixel. Thereabouts.
All right, great. And then C asks, how many more targets in Crater 2 can be observed with GHOST for this kind of analysis?
That's a great question. These are just two of probably somewhere between the tens to 100 stars that we could actually probably probe in Crater 2 at similar or slightly fainter magnitudes. So there is a promising prospect for actually being able to map out the chemical abundance pattern of this galaxy.
Any other questions? If not, let's thank Chris again.
Thank you all.
And then up next, we have CE Shu talking about, I believe, a deteriorating asteroid.
Yeah, thank you, Zach. Let me have my screen. Great pronunciation by my name, by the way. Thank you. Just making sure that can you see my screen? Okay, all right. I'll get started. Good morning, good afternoon, good evening, everybody. Thank you for being here. My name is.
There's a little. Sorry. Oh, wait, there was a build order thing. Yeah, in the lower right. That was popping up.
Oh, let me just. Is this okay now?
Yep, it's gone.
Okay, okay, awesome. All right, thank you. Yeah. Yeah, so my name is Siyi Xu. I am an astronomer at Gemini Observatory and NOAA Lab. I'm very glad to be here and to share with you some of the results from GHOST-SV, which is a really cool and fun project. Thank you everybody for getting involved to make it happen. Like Chris, I really enjoyed working in GHOST-SV and have learned a lot. So the topic of this talk is I'll tell you the story about a white dwarf with a disintegrating asteroid. And all the data is actually in this GHOST SV program. And the raw data has already been in the archive. And we are hoping to provide the reduced data very soon. So if you're interested in checking it out, please go ahead. Yes, so white dwarfs. First, let me tell you about this one of my favorite white dwarfs, WD1145 plus 017. I guess for people who don't know me, I work on planetary systems around the white dwarfs. You know, they are not just dead stars. There are kind of a lot of interesting things happening. Though in this case, it is a disintegrating asteroid. So you might ask why, because it sounds pretty crazy. So this system was actually first identified by the extended Kepler mission, like K2. And this is the K2 light curve. So it covers about 80 days. And then when you actually look at the 80-day light curve, you can see some crazy things happening. So here is a light curve binned by every 4.5 hours, which there seems to be a signal repeating itself every 4.5 hours. So it's very, very short. And the 4.5 hours is actually right within the tidal radius of the white dwarf. So any objects there kind of will be disintegrating. Right? And another interesting thing about the K2 light curve is you can already see changes through this 80-day observation. Like in the beginning, you kind of don't see much. And then maybe in the middle, you start to see a transit feature. And then later it's gone again. And then when the signal was first identified, people were really confused, be like, okay, what's happening? So it was followed up with ground-based observations. And here is how the light curve looked like. So because the light curve is really smeared out in the K2 light curve, right? So now you can really see there is a very deep transit. It goes down to about 40%. So very, very deep. And also the shape of the transit, it doesn't look like a solid body. It's really much more like a solid body with a dusty tail. So we know, there must be something interesting happening. And because this is a relatively bright target and with such high transit depths, this system caught the interest by a lot of amateurs. So this is one of them, Bruce Gary, actually have been following this system since 2015. He's also my oldest collaborator. He's over 80s, but he's still like very interested in having his own telescope in the backyard observing this system. So this is a light curve for one observing season. So time goes from bottom to up. And each light curve was phase folded together, and then they are separated by about 1 month apart. So to me, it's just amazing how much the light curve looks different, right? From month to month. Like if I show you two, you probably wouldn't say these are the same object, but it's really the same object. And so our best hypothesis is there is really an asteroid in the process of disintegrating around this white dwarf. And we are just seeing different fragments kind of transiting the white dwarf. And that's how, this is the first one of its kind. Now we have found a few more. And that's how the system is quite interesting. So for me, I mostly do spectroscopy, and actually just by chance, about the same time around the discovery, I also observed this system with Keck HIRAS. I was more interested in the spectroscopy part of this system. And actually, I find this white dwarf to be pretty unique than what I usually know. So here I'm showing Keck HIRAS data. The black line is the data. And then so you can see I'm focused around calcium K-line, iron, chromium, nickel. And then I was expecting to see those narrow photospheric lines from the white dwarf's photosphere because I was looking for polluted white dwarf. I did see them, but you see those also this broad things around it. And at first I saw these are instrument artifacts, and I tried very hard to reduce the data to get rid of it. But after trying many times, I realized I can't get rid of them. They seem to be everywhere. I'm like, oh, okay, maybe this is actually a real thing. So I looked a bit more into that. I worked with collaborators trying first to model the photosphere of the white dwarf. So which is this red line, because we do have some lines that do not have these broad features. And then after I subtract the photospheric line from this observed data, we are left with this magenta line. So there seems to be quite a lot of additional absorption around this system. So some lots of analysis, we think, okay, our best hypothesis is maybe we're seeing circumstellar gas around this white dwarf. And the gas is actually not in a circular orbit, because if it's circular orbit, and since we're seeing absorption, right, we're only seeing this part, we'll be seeing a symmetric component. But right now, we are actually seeing an eccentric disk around the white dwarf. And then the velocity span is actually from minus 100 kilometer per second to plus 200 kilometer per second. So it's actually pretty close to the white dwarf, like actually closer to the 4.5 hour transit period we're seeing. This is the first one of its kind, showing this kind of weird circumstellar lines. So we did a bunch more observations. Actually, we started a spectroscopic campaign trying to understand what's happening. So we have used Keck HIRAS, ESI, and the VLT X shooter because we really want to know kind of what's happening with the circumstellar line. It's quite interesting. The lines are actually changing. So here I'm showing iron, magnesium, silicon line. For magnesium and the silicon, we did not have any circumstellar line component. So you see the photospheric line actually fits pretty well, which is our red model. But if you see the iron line, the circumstellar component is really changing. Like in our discovery paper, we saw both the blue shifted and the red shifted component. But then like later, it seemed to go to a more red shifted component. And then it's coming back to only blue shifted component. So maybe we're actually seeing a processing disk around it, which is also interesting because the orbital period is only hours, right? But the disk seemed to be there continuously for several years. Anyway, then when this GHOST SV opportunity comes up, we're like, okay, maybe we should check out this object. Haven't observed it in a while, wondering what is the circumstellar line doing. And also we have so many other comparisons with other spectrographs. So this is our basic setup. We used similar to Chris setup actually. We use the standard resolution mode, which is about 55,000 resolution. We use the dual target mode. So we have one IFU on target and the other IFU on sky. The white dwarf is a point source. It's 7.3 magnitude. We required decent weather conditions, image quality of 70 percentile, and a cloud coverage 70 percentile, and a sky background of 80. We actually did 3 30-minute exposures. So I want to say the first 2 was within spec, but the last one, the condition really deteriorated because a lot of cloud come in. Then we used the 1/2 binning. We also observed the flux standard with the same setup. Data reduction was done with Dragons. This is a slightly earlier version of Dragons, so the result you will see here. We also re-reduced it with the latest version, and the difference is small, but I haven't done a more comprehensive comparison yet. All right, so what have we seen? So first, feel like I'm doing some GHOST and HIRAS comparison. So for people not familiar with HIRAS, it have 2 collimators, so you can only do blue side or red side at a time. You can't really do them simultaneously. Okay, that's one advantage of GHOST. So for all the HIRAS observations, and I was using the C5 Decker, which have a slit width about 1.1 arc second and a spectral resolution about 40,000. So HIRAS have a slightly lower spectral resolution compared to GHOST. Anyway, so for me, this is around about the bluest I can go with GHOST. So we do see calcium K line, right? But I guess because the coating of our mirror, the overall like sensitivity in the blue side is not as good as HIRAS. But we did capture like the overall shape. And in this case, I actually picked an epoch where the circumstellar line looks almost the same. So you can see like the overall shape and everything, it agrees pretty well. And the GHOST observation is a little bit longer than the HIRAS exposure. Right, now we move forward. So remember, this is like calcium K is about my like bluest part I can get reasonable signal to noise ratio. And then we move a little bit to longer wavelengths. When you go to like above redwood of 4,000, it seems the signal to noise ratio is already comparable. And then when you go to say even longer wavelengths, so this is the calcium infrared triplet, it seems like, and here the exposure time between GHOST and HIRAS red is the same, and it seems the GHOST have a higher signal to noise ratio compared to HIRAS. And since we do have the flux standard, I can also take a look at the flux calibration. So wavelength, flux, and this is the GHOST blue and red, and this is the white dwarf model. So I guess overall, we do capture the same shape and stuff as expected for the white dwarf. But I think particularly on the blue end, we do have some parts that the absolute flux seems to be like a little bit different than what we would expect it. But I think the good thing is it does capture the relative shape of the white dwarf spectrum. Okay, so going back to the science, what did we see really? So when I stack all the spectrum together, this is again focusing around the iron 2, like a 5169 line, and the black line is the GHOST data. And then we have show some models, which is actually done by Erica, a collaborator at the University of Montreal. So you can see the red line is our best fit white dwarf photospheric model. And then the blue line is a disk model. So we are using basically a bunch of eccentric rings to fit this model. And then remember this extensive survey we done? If you look closely, so this GHOST data was taken in May 2023. It actually looks pretty similar to the data we took in May 2018. So that makes this longer baseline really make us think, okay, so maybe the precision period of this system is actually about 5 years. So we are working on basically putting all the data together to model the disk, what's happening with the disk. And another interesting thing, since at the same time, Bruce is still observing the system, the transits seem to be gone. So this is a light curve taken at the exact same time, like in May, like basically 2 months ago. It's basically flat. So so basically, we're not seeing any transiting activities right now. However, the circumstellar lines are still there, which is a little bit puzzling. Right. That brings me to the summary of this talk. I present to you ghost observation on a point source. It's an interesting white dwarf. We find the overall performance is pretty similar to Keck HIRAS. I mean, certain part a little bit better, certain part a little bit worse. But I think another advantage is we really have the full wavelength coverage in one go. Right? And then about this specific white dwarf, we find that the transits are gone, but the circumstellar lines are still present and processing as usual. With that, I just want to say thank you for your attention, and I'm happy to take any questions.
All right, thank you. Yeah, please put any questions in the chat, or if you just want to raise your hand and ask them verbally, that's okay as well. So I wait for a couple more questions. So you said that you had X shooter data on this object. Did you happen to have time to do a comparison between that and the ghost observations, or?
Yeah, I mean, I don't have it here. I guess I did try to overlay them, but the thing is, the X shooter spectral resolution is lower, right? It's only like 6,000. So it just, I mean, I guess, yeah, I think this one is actually X shooter. So you can see, like, so I don't think the comparison is as really promising, but I feel like maybe the best comparison here doing is between ghost and HIRAS. Yeah.
Yeah, Stephanie.
Hi, nice talk. See, this is completely not my field, but I was curious. So when you say that the transit is gone, like, so what are the physical scenarios then to explain this?
Right, exactly. Yes. So basically the question is, what's happening to the transits, right? Why are they gone? So just my understanding is like what's causing the transits is really more like a fragment made mostly of dust. That's why like kind of every 4.5 hours, every time we see them, it looks actually quite different. So I think each fragment really only lasts a few weeks to a few months. So once the fragment is completely disintegrating, then we don't see that particular transits anymore. So I think the asteroid parent body is still there, orbiting around the white dwarf and slowly disintegrating. But exactly like how do the fragments fall off and when does it start to producing transit features? I think it's much more complicated, and I don't think we really know. But I think from kind of the light curve monitoring we know like the transits are highly variable, right? So it can be very active sometime and then it can be gone and then it might come back again. So yeah, so it's, but I think it maybe to me, like a little bit puzzling thing, if the gas is directly coming from the fragment which caused the transit, right? It seems like if the transits are gone, I feel like the gas probably will be gone pretty soon too. But it seems like the gas is still there or just being undisturbed, like doesn't care about what the transits are doing, just doing its own precession thing.
So just to kind of follow up, so then it means it's still worth to keep monitoring to see if the transit comes back based on what you said. Okay.
Yes.
Okay.
Yes.
Cool.
Yes. Yeah. So the amateur is very on top of that.
Oh, nice.
Bruce says that's his favorite object, and he will keep observing it every night. So yes.
All right.
Thank you.
Thank you.
Jung-un?
Yeah, hi Steve, thank you for your talk. And I wonder, for your analysis, you use a normalized spectrum like this table, but why did you take the standard star for rough calibration that is useful for other analysis?
Okay, yes. So I guess Joanne is asking for my own analysis. Yes, I mostly use a normalized spectrum. So the absolute flux kind of does not matter. I guess I take the flux standard and more like I'm just curious how good is the flux calibration routine in general. So that's why I took a flux standard and I just want to kind of test. I guess I don't have the result here, but I also do have kind of the flux calibrated spectrum of X shooter, and I compared it with the white dwarf model. I think it's pretty similar. Just in the blue end, it's just very difficult to get the absolute flux right. So I would say the absolute flux calibration may be good within 10%. Like that's kind of how it is. Yeah, but I agree. Depending on what you are trying to do with your science, you might not need to spend time to do your flux calibration, flux standard.
Yeah, I wanted to ask you if you have another flux calibrate spectra, previous one, then if take a look at that and
Right. So yeah, I think that's a good point. So there are other flux standard taken like during SV, so I can give it a try and to see if I can kind of improve the flux calibration, right? So I have not done that, but I think because generally speaking, like even in this case, the white dwarf was observed one night, and then the flux standard is observed another night, right? And then so that's why I feel like the absolute flux calibration will just be difficult. But yes, you're right. I should try the other flux standard and just to see if it can improve it. Thank you.
Yeah, I had another question. So you mentioned, and I may have misheard, but you found more of these systems. So do they all show this? Have any of the other ones shown this just drop off in the transits, or are they still pretty much constant, or still maybe not constantly, but still transiting at certain points?
Right. So this is the first one that discovered by K2. And since then, there may be another 5 or 6 systems actually discovered by ZTF. And in comparison, I think those ZTF ones is much weirder, actually. Like here, the period is 4.5 hours. And the ZTF ones, some of them have period like over 100 days. And their transits actually last for like weeks. And a lot of the systems, we haven't even figured out the period yet. You just see like a very weird, so the light curve is even weirder. So my take of that is because maybe those are even in the earlier stage of the tidal disintegration. So in this system 1145, the fragment has, or the asteroid has already been circularized, right? So it's more later stage, but at the earlier stage, maybe they are still on a very eccentric orbit. So like materials still keep coming in. So yeah, the other systems are even weirder.
So the
in terms
other,
of the light curve. Yeah.
okay, do the other systems show the deterioration still, or is it more just like there's the body of transits just?
Well, what do you mean deterioration? Oh, you mean the,
or disintegration, sorry.
so I think the other thing is basically just the light curve looks weird. Basically, because white dwarf, usually you don't expect much happening, right? Like it's a flux standard, it's very steady. The other thing is basically shows very weird light curves that most of them do not have periodicity yet.
Are there any other questions? Any questions for either of our presenters today? If not, then I'm going to say thank you all for coming. And I'm going to say that we have another one of these webinars next week with different speakers. These webinars will be posted onto the webpage as well. So if you miss the next one, please check out the webpage for the presentations in the future. So thank you very much.
Thank you for hosting.